we're looking at section 4.3 here in pre-calc. This is about right triangle trigonometry. So we've seen that in a unit circle, the radian measure of a central angle is equal to the measure of the intercepted arc. Thus the value of the trigonometric function at the real number t is the value at an angle of t radians. So let's say we have an angle on our unit circle. This one in particular measures pi over 3 radians, and so it's got an intercepted arc that's also pi over 3. So we're going to go ahead and just drop a line segment. We take that point with that angle of pi over 3 on the circle, we drop it down, and we've created a right triangle. So we can think of that pi over 3, or that 60 degrees, as the measure of an acute angle at that point in the right triangle. So because sine of t is the second coordinate of the point P and cosine is the first coordinate, we can see that sine of pi over 3, or sine of 60, is the y value, or y over 1, because that's the length of the hypotenuse, which is also the radius. Same thing with our cosine. So cosine of pi over 3, or cosine of 60 degrees, is the x coordinate at that point, which is really the same thing as x over 1, 1 being that hypotenuse, which is, again, that radius of the circle. So in solving certain kinds of problems, it's really helpful to interpret trigonometric functions in right triangles, where angles are limited to acute angles. So this is a throwback to the right triangle trig you've done in trigonometry. So the figure over there to the left shows a right triangle with an acute angle labeled theta. The side opposite the right angle, the hypotenuse, has the length of c. The other sides of the triangle are described by their position relative to that acute angle theta. So one side is opposite of theta, and then one side is adjacent. So this is where our definitions come from. You have seen this before in geometry. So sine is the ratio of opposite over hypotenuse. Cosine is the ratio of adjacent over hypotenuse, and tangent is the ratio opposite over adjacent. And then the other three trig functions are those reciprocals of the sine, cosine, and tangent. So this is just a good reminder, even though we're working with the unit circle and having these values, sine, cosine, and tangent all are still always going to be coming from this idea of this ratio that's constant. We'll see that in just a minute. So a reminder of how we can remember these definitions is that phrase SOHCAHTOA. So the so part represents sine being opposite over hypotenuse. Ka is our cosine adjacent over hypotenuse, and toa is our tangent, which is opposite over adjacent. So notice here we've got 4 different triangles that are 4 different sizes. The theta is the same angle in all 4 triangles. So this is saying it's measuring about 56.3 degrees. So they all have the same shape, and when they take the lengths of the corresponding sides, they're all in the same ratio. They're all going to reduce to the same fraction. So in each triangle, the tangent function has the same value for the angle. But notice, even though all 4 of these triangles are different, coming with that same angle of theta, the ratios are all going to reduce to be the same thing. So in general, the trigonometric function values of theta depend only on the size of the angle and not on the size of the triangle. So we are going to use this right triangle trig to find the values of the 6 trigonometric functions for the triangle that we have here. So notice how we're given only 2 sides of the triangle. So we're going to have to remember our Pythagorean theorem. So Pythagorean theorem says a squared plus b squared is equal to c squared. And that c is always going to be our hypotenuse. That's the one that's by itself. So to find this, we can take our a, which is 5, plus our b, which is 12. And we know that's going to be c squared. Now, you can do this on your own, check it in a calculator. But this is one of our common right triangle side lengths. This is a 5, 12, 13 triangle. Once you start to recognize these, you wouldn't need a calculator. We like these ones because they're always going to give us whole numbers. 3, 4, 5 is the most common you'll see. 5, 12, 13, though, is another one. So our C here is going to be 13. So we have to make sure we're referencing the angle that we're using, okay? So our angle here is theta, because depending on which angle you use, you're going to get different ratios for your trig function. So when I use this angle theta that's there, sine of my angle theta there is going to be my opposite, so the angle opposite theta, which is 5, sorry, the side opposite our angle, 5 over our hypotenuse, 13. Cosine of theta is adjacent, 12 over hypotenuse, 13. And tangent of theta is opposite over adjacent. So that'd be 5 over 12. So then we can find each of their partner functions by doing the reciprocal. So sine goes with cosecant. So that would be 13 over 5. Cosine goes with secant. So that would be 13 over 12. And tangent goes with cotangent. So cotangent of theta would be 12 over 5. Okay, we've got a different angle here. So this time we're still missing a side length, but it's not the hypotenuse this time. So we're gonna have to put in a little bit more work. So when we do our a squared, that's 1 squared, plus b squared is going to be c squared, which is 3, so 3 squared. So that's 9. We're gonna have to subtract the 1. So we know that b squared is gonna be 8, which means that b is square root of 8. Now we do like to have simplified answers here, so we can reduce or simplify square root 8. 8's the same thing as root 4 times root 2, and so this would simplify to being 2 root 2. So again, we pay attention to that location of our theta as we now find our trig functions. So sine of theta, opposite would be 1 over hypotenuse 3. Cosine of theta is adjacent to root 2 over hypotenuse 3. And tangent is opposite over adjacent. So that's 1 over 2 root 2. Now, if we're wanting to rationalize our denominator here, our issue there is lying in the radical part. So we would multiply by root 2 over root 2. And so we'd end up getting root 2 over 4. The root 2's in the denominator would multiply to get to 2 times the first 2 that's already there to get us to the 4. Okay, the other 3 trig functions, so then cosecant would be 3 over 1, or just 3. Secant would be 3 over 2 root 2. Same idea though, if we want to rationalize that denominator, multiply by root 2 over root 2, we end up with 3 root 2 over 4. And then cotangent, we're going to flip it. So again, our denominator here is just going to end up being 1. So cotangent would just be 2 root 2. So if you've seen the unit circle, you know that there's certain trig values that we have first. We've got some special angles that we're going to see, pi over 6, pi over 4, and pi over 3. So those are the special ones that we want to talk about and find how we can find those ones. So we used the unit circle before to find the trig values at specifically pi over 4. How can we do those using a right triangle? Well, so hopefully you remember your special right triangles from geometry. If not, they've got them drawn for us here. So a right triangle with a 45-degree angle is going to have a second 45-degree angle. It's a 45, 45, 90. So it's isosceles. So the two sides that are across from the two congruent angles are going to have the same length. So just for ease of use here, they called those two same sides 1. And so when they found the hypotenuse, they found that it would then end up being square root 2. So if we've got our 45-degree angle, and with this one, it doesn't matter which angle you use because they're the same, right? But we'll use the one that's labeled. We're just finding sine, cosine, and tangent here. So sine of 45 degrees, which is the same thing as sine of pi over 4, is going to be our opposite 1 over hypotenuse, which is root 2. So again, if we were to rationalize, multiply by root 2 over root 2, we'd end up with root 2 over 2. And then cosine will be the same thing, because our adjacent, cosine of pi over 4, our adjacent side is also has a length of 1. And so we end up with the same thing of root 2 over 2. And then tangent being opposite over adjacent, since those values are the same, we get 1 over 1, which is just 1. Same idea here for helping us find sine and cosine of our other special degrees here. So we want to find sine and cosine of 60. We're going to start there. Let me slide over to my highlighter. So our 60 degrees, that's pi over 3. So sine of 60 degrees, just the same thing as pi over 3. is going to be opposite, that's square root 3, over hypotenuse, which is 2. And then cosine of 60 degrees is the side adjacent to our 60, which is 1 over hypotenuse, which is 2. Now I need to switch my color here because now we're looking at a different angle. So now we're looking at the 30-degree angle. So when I compare that to my 30-degree angle, my sine of 30 degrees, which is pi over 6, now the side opposite of the 30 is the 1 over hypotenuse of 2. And my cosine of 30 degrees, or cosine of pi over 6, the side adjacent to the 30 degrees is that root 3. So we end up getting that root 3. So these are the ones you're going to know, want to know. These are the ones that are going to show up the most often. And these are what you're going to use later on to use reference angles. And so it helps to memorize these. And these are on your unit circle. So if it helps to look at them in a chart or look at them on the unit circle, that's up to you. Some things I like to point out. This is what helps me remember kind of the order on things. Notice that all of these denominators on sine and cosine, they're all 2, which is helpful. So those are all going to stay the same. When we look at the sine numerators, as our angles get bigger, our numerators get bigger on sine. If it helps, you can notice, hey, they're all square roots, right? The square root of 1 is 1. And so square root 1, square root 2, square root 3, all with the denominator of 2. Whereas with the cosines, it's actually going to go the opposite direction. So the same values, just going in the opposite order, root 3, root 2, and then 1. As long as you know sine and cosine, you can figure out tangent by doing sine divided by cosine. So just learning this pattern should hopefully make it easier for you with that memorization aspect. So again, sine's going to be going up in value, cosine's going to be going down in value. 1, 2, 3, and 3, 2, 1, and they're all divided by 2. All right, we have this idea of cofunctions. So the value of a trigonometric function of theta is equal to the cofunction of the complement of theta. So complement, if you remember your geometry, are the angles that add up to get to 90 degrees. So cofunctions of complementary angles then are equal. So these are the cofunction identities. Sine of theta is equal to cosine of 90 minus theta. So that means cosine of theta is equal to sine of 90 minus theta. So sine and cosine are buddies in this sense. Tangent and cotangent are buddies, and secant and cosecant are buddies. So if we're in radians, as always, we're going to replace that 90 degrees with 8 pi over 2. So if we want to find a cofunction with the same value, if we've got sine of 72 degrees, that's going to be the same thing. Its buddy is cosine. So cosine of 90 minus 72. So that would be cosine of 18 degrees. It's going to have the same value as sine of 72. And then with B, we've got cosecant of pi over 3. So cosecant's buddy is secant. We take secant of pi over 2 minus pi over 3. So this is where you hopefully know your fractions. We would need a common denominator of 6 here, right? So pi over 2 is 3 pi over 6, and pi over 3 is 2 pi over 6. That means this would be equal to secant of pi over 6. Now, when we deal with right triangles, that also leads us into this idea of word problems, right, and some applications. Super useful. Many applications of right triangle trigonometry involve the angle made with an imaginary horizontal line. So as shown in the figure below, an angle formed by a horizontal line and the line of sight to an object that is above the horizontal line is called the angle of elevation. So if you're at the horizon and you're looking up, it's the angle of elevation. The angle formed by a horizontal line and the line of sight to an object that is below the horizontal line is called the angle of depression. So this is a good visual on how you can determine which one you're looking for, if it's angle of elevation or angle of depression if you're looking up or looking down. So sighting the top of a building, a surveyor measured the angle of elevation to be 22 degrees. The transit, so that's the tool that they use to measure these things, is 5 feet above the ground and 300 feet from the building. Find the building's height. I'm a little silly, and I like to usually draw a picture to go with these types of word problems. So we're looking for the top of the building, right? So there's my building over here. Some nice windows on it. So it should probably have a door. And then we've got somebody who's measuring. So we've got a surveyor. And if you've ever seen surveyors, you'll know they've got a little tool that they're going to use. It's on a tripod. I promise it's not the same as my stick figure guy. But that's what's measuring the angle of elevation to that top of the building. Now they're telling us this would be our horizon then for that transit. So this angle here is our 22 degrees. They're telling us the transit is 5 feet above the ground. So this tool is 5 feet above the ground, and it's 300 feet from the building. This distance here is going to be 100. So that's also the same distance as that part of our triangle that we've created. So we're trying to find the height of the building. So ultimately, this is what we're trying to find. But notice we only get to use part of that from our triangle. So let's go ahead and call this missing piece X, because that's what we like to do. So looking at just the triangle portion, I have an angle, and in relationship to that angle, I have the side that's opposite, and I have the side that's adjacent. So in order to solve this, I need to use the trig function that has opposite and adjacent. So that's where I'm going to use my tangent. So I'd say tangent of my angle, which is 22 degrees, is the side opposite, which is what I'm calling X, over my side that's adjacent, which is 300. So all I need to do to solve for X, I'm going to multiply by that 300. So X is 300, tangent of that 22 degrees. And from my calculator, making sure I'm in degrees mode, I did calculate that height there was 121 feet. But this is where we have to be careful, because this machine isn't coming from ground level, whereas the building is. So this is where that extra 5 feet is coming into play here. So we have to make sure and take that height and add that into it. So we have to take the 121 from the triangle that we formed and then add on the 5 feet for that height of our tool to get the total height of the building to be about 126